In this video, I'll be talking about ownership and lifetimes. Lifetimes are a way to specify to the compiler how to handle borrowed data, and this will enable you to store borrowed data in structures and return borrowed data from functions. Before we dive into lifetimes, let's have a quick review of ownership. All data in Rust must have an owner, and the owner is responsible for cleaning up data. This is how Rust handles memory management. By default, data can only have one owner. It is possible to have multiple owners, but that is covered in a later lesson. Functions, closures, structures, enumerations, and scopes are all owners of data. So whenever you store data in a struct or send data to a function or closure, those become the owner of that data. Data can be moved from one owner to another through assigning variables and through calling functions. It is also possible to borrow data from an owner, although the owner still needs to clean up the data. Borrowing is done using the ampersand symbol, and the code borrowing the data is never allowed to clean up that data. Let's take a look at some example code. On the right, we have a frozen item and a freezer. On the left, we have a place item function, and it accepts a mutable freezer and a frozen item. So this function is going to be placing these items into this freezer. And in our main function, we just create a freezer, a frozen item, and then we place the item using the function. When we call the place item function, we let it borrow the freezer, and then we're moving the cube. So there's no borrow here. Since we are moving the cube, the place item function is responsible for cleaning up that cube. So the cube will move here, and then this function is responsible for cleanup. The place item function is only borrowing the freezer, so it's borrowing it, therefore the place item function cannot delete the freezer. In the place item function, we have our borrowed freezer here, and we move the item, which is an ice cube in this case, into the freezer structure. And that's done here on this first line. So we have a borrowed freezer, we access the contents, and then we're pushing this item into the freezer. The ownership of this frozen item has now changed, and the freezer is now the owner. So the place item function cannot clean up the item anymore. The freezer itself has to do so. At the end of the main function here, there's no more code. So once the main function ends, the freezer will get cleaned up because the main function is responsible for cleaning up everything that's created within. Now that we've reviewed ownership, we can take a look at lifetimes. Lifetimes are a way to inform the compiler that borrowed data will be valid at a specific point in time. Lifetimes are needed for storing borrowed data in structures or enumerations and returning borrowed data from functions. All data has a lifetime, but the compiler is able to automatically calculate the lifetimes in many cases, so you don't always see them in code. Let's take a look at the lifetime syntax when working with a structure. We have the struct keyword here, followed by the name of the structure. Lifetimes are a form of generics, so we use the same syntax as a generic type. So we have our less than and greater than symbols, and some stuff in between. Here we have a lifetime called tick A. So the tick is just an apostrophe, so tick A is the name of the lifetime. Lifetimes are usually named tick A, tick B, and tick C, similar to how generics are named T, U, and V. Generic lifetimes aren't restricted to just single letters either. You can name these anything you want except for tick static. Tick static indicates that the data exists in memory for the entire duration of the program. Within this structure, we have a single field that's using borrowed data. We indicate to the compiler that the borrowed data has the lifetime of tick A by placing it directly after the borrow symbol, which is the ampersand. This tick A is an indication to the compiler that the data will still be around after this structure has already been destroyed. Let's help understand this better by seeing an example in a complete program. So here we have a part, which is going to represent like a machine part or car part. We then have a robot arm, which is borrowing a part. And we have an assembly line, which just contains a series of parts. In our main function, we're just creating a new assembly line, adding some parts to it. And then here, we create a new robot arm, and that arm borrows one of the parts from the assembly line. Our assembly line contains two parts, a bolt and a panel. We create a new scope here, and within the scope we have our robot arm, and it is borrowing the first part here, so it's borrowing a bolt. Since the robot arm is borrowing a part out of this vector here, we have to use the ampersand symbol to borrow it, and in addition, this robot arm structure has to have a lifetime annotation. In this case, we're using tick A as our lifetime annotation. The tick A is telling Rust that this part exists before the existence of this robot arm. Therefore, we're able to access it. After this robot arm is done borrowing the part, code will execute here, and the robot arm will be destroyed because this scope ends. So this robot arm is going to go away when we reach this point. However, the assembly line still exists because the assembly line was created here and it's still going to exist down here. That's why we were allowed to borrow within the structure. So the tick A is telling Rust that, hey, we created an assembly line earlier and it's still going to be valid here when we want to borrow it. Now we'll take a look at the syntax for including lifetimes in a function. Just like with generic types, we create a new lifetime here called tick A, surrounded by the less than and greater than symbols. We then just use tick A whenever we have a reference that utilizes borrowed data that will outlive this function. We also sometimes need to use lifetimes in functions if we want to return a field from a structure as a reference. Using lifetimes in functions isn't too common because the compiler is able to figure it out most of the time. But if you do need to use one, this is how you would do it. Lifetimes are a difficult to grasp concept and may take multiple failed attempts at utilization until you get the hang of it. This is normal and expected, since the concept, while not new or unique in programming, is new in the way that the Rust compiler is able to enforce the idea. Here are a few phrases you can remember, which may help increase your understanding of lifetimes. Lifetime annotations indicate that there exists some owned data that lives at least as long as the borrowed data. So let's say you create a structure and you want to borrow from it. You'll have to ensure that the structure lives at least as long as that borrow in order to use it, because if you delete the structure, then you can't borrow from it because it's been deleted. There exists some owned data that outlives or outlasts the scope of a borrow. So if you create some data and you create a new scope, then within that scope, you can borrow as much as you want. Once that scope ends, your borrow is destroyed, but the data you created before the scope is still lying around. So that's totally okay to do. There exists some owned data that exists longer than the scope of a borrow. So you can, for example, create a configuration structure in the beginning of your program, and then later in your program, borrow from it without issue, or store borrowed data from it, no problem, because that configuration exists longer than that scope. Structures utilizing borrowed data must always be created after the owner was created, and they must always be destroyed before the owner is destroyed. This is consistent with the ideas above because you're unable to borrow from something if it's been destroyed. So the thing you're borrowing from must exist before you borrow from it, and it still has to be lying around after you're done borrowing from it. To recap, lifetimes allow borrowed data within a structure, and they allow returning references from functions. Lifetimes are the mechanism that tracks how long a piece of data resides in memory. Lifetimes are usually elided, but they can be specified manually when needed. And lifetimes are checked by the compiler. If you use a lifetime incorrectly, the compiler will emit an error.